In this video, we're going to learn how to find the vertical asymptotes of rational functions. We saw in our last video that asymptotes were lines that our functions approached when we traced the graphs. Rational functions have vertical asymptotes when the function goes up to infinity or down to negative infinity as the x values go towards some finite number. Let's take a look at an example. In example A here, we want to find the vertical asymptotes of the function f of x equals x squared plus 2x minus 3 divided by x squared minus 1. If we want to find vertical asymptotes, we want to think under what circumstances will the outputs of my function f of x go to positive or negative infinity. Now, when we're dealing with a fraction, we can ask ourselves, under what circumstances will this fraction get larger and larger? One possibility is that our numerator gets larger and larger. But when we're thinking about vertical asymptotes, we're plugging in x values that go towards a finite number. So no matter what finite number we plug in for x, the numerator here can only get so large. What I mean by that is our numerator can't grow without bound as we plug in x values that get closer and closer to some finite number. So you might now ask yourself, what is another way that a fraction can get larger and larger? Our second option is if the denominator here gets smaller and smaller. For example, if your numerator is some finite number like 10, and your denominator gets smaller and smaller, getting closer and closer to 0, the size of your overall fraction will get larger and larger. This is why in our previous video we saw that vertical asymptotes seemed connected in some way to the x values that made the denominator equal to 0. So let's start by figuring out which x values make the denominator equal to 0. We can just set the denominator x squared minus 1 equal to 0 and try to solve this equation. On the left here we can factor this since it's a difference of squares. This factors as x plus 1 times x minus 1. This is equal to 0. Then, if we have a product of two things and it equals 0, that tells me that either the first factor equals 0 or the second factor equals 0. So we have x plus 1 equals 0 or x minus 1 equals 0. On the left here, if we subtract 1 from both sides, we get x equals negative 1. On the right, if we add 1 to both sides, we get x equals 1. So when x is negative 1 or when x is positive 1, the denominator equals 0. So if we plug in x values that are close to negative 1 or close to positive 1 into the denominator, we're going to get numbers that are close to 0. Let's now take a look at the graph to see if we have vertical asymptotes at both of these x values. So let's type in our function. We have x squared plus 2x minus 3 divided by x squared minus 1. So this here is the graph of our function. We notice that there is just one spot where the graph goes down to negative infinity and up to positive infinity. So there seems to be just one vertical asymptote, and it occurs when x gets closer and closer to negative 1. So let's enter that line in, x equals negative 1. And we see here, when we trace our graph towards negative 1, the y values or the outputs go down to negative infinity on this side. If we're on this side and we trace towards negative 1, the graph goes up to positive infinity. So x equals negative 1 is indeed a vertical asymptote for our function. The question is, how come we didn't get a vertical asymptote at x equals positive 1? The reason has something to do with the numerator. So let's think about what happens when we plug in x values getting closer and closer to negative 1 and positive 1 into our function. So as x goes closer and closer to negative 1, our function f of x, which is x squared plus 2x minus 3 divided by x squared minus 1, we know that the denominator is going to get closer and closer to 0. What happens to the numerator as we plug in numbers that get closer and closer to negative 1? Well, plugging in negative 1 into the numerator, we get negative 1 squared plus 2 times negative 1 minus 3. So that's positive 1 minus 2 minus 3, which is negative 4. So our numerator gets closer and closer to negative 4. So if we take a number that's close to negative 4 in the numerator and divide it by a number that's close to 0 in the denominator, the smaller the denominator gets, the larger the overall fraction gets. That's why our outputs are going towards either positive infinity or negative infinity. Now, on the other hand, we can consider what happens as we plug in x values that get closer and closer to 1. Our outputs, f of x, which is x squared plus 2x minus 3 divided by x squared minus 1. Well, we know that the denominator will get closer and closer to 0, but what happens to the numerator? Well, plugging in 1 into the numerator, we have 1 squared plus 2 times 1 minus 3, which is 1 plus 2 minus 3. That's going to go towards 0 as well. Now, when we have a fraction and the numerator goes to 0 and the denominator goes to 0, it's a little bit harder to say what happens to the overall fraction. What we do know, though, is that when we plug in x equals 1 into the numerator equals 0, which means that from the factor theorem, we know that the numerator has a factor of x minus 1. Similarly, if we plug in x equals 1 into the denominator, the result is also 0. And again, from the factor theorem, we know that the denominator has a factor of x minus 1. So let's take a look at a factored version of our function. Our function f of x is x squared plus 2x minus 3 divided by x squared minus 1. We already know that the denominator is a difference of squares, so it factors as x plus 1 times x minus 1. The numerator, if I want to factor that, we need two numbers that multiply to negative 3 and add up to positive 2. Those two numbers would be positive 3 and negative 1. So our numerator factors as x plus 3 times x minus 1. Now, as long as x is not equal to positive 1, we can cancel these common factors out, which tells us that our function f of x behaves just like x plus 3 divided by x plus 1. And we can confirm this on the graph. If we were to graph the function x plus 3 divided by x plus 1, we see that our green graph overlaps my purple graph, which means they're essentially the same graph. And now we can see why there's no vertical asymptote for f of x as x goes to 1. Because as x goes to 1, if we look at the function x plus 3 divided by x plus 1, as x goes to 1, the numerator goes to 1 plus 3, which is 4. And in the denominator, as x goes to 1, 1 plus 1 gives us 2. So overall, our fraction becomes 4 over 2, which is just 2. The size of our fraction does not go to positive infinity or negative infinity. That's why we don't have a vertical asymptote at x equals 1. Instead, in the graph of our function, we see that the graph approaches the point 1, 2. But if we actually trace the function in Desmos, we see that as we get to 1, our graph is undefined at x equals 1. This is because x equals 1 is not part of the domain of this function, since it makes the denominator of our fraction equal to 0. Which means what we have here is a hole. So in this problem, we have a vertical asymptote, which I'll abbreviate with VA, at x equals negative 1, and we have a hole at x equals positive 1. From our example here, we see that when we're trying to decide the vertical asymptotes for a rational function, what we want to do is factor both the numerator and denominator and cancel out any common factors. That way we can tell when the denominator goes to 0 without making the numerator go to 0 as well. Let's look at a couple more examples. In example B here, we want to find the vertical asymptotes of the function g of x equals x squared plus 5x minus 14 divided by x squared minus 5x plus 6. Again, if we want to find any vertical asymptotes, what we want to do first is factor the numerator and denominator and cancel out any common factors. So for our function here, g of x, our numerator is x squared plus 5x minus 14. If I want to factor this, we need to come up with two numbers that multiply to negative 14 and add up to 5. Those two numbers would be positive 7 and negative 2, so our numerator factors as x plus 7 times x minus 2. In our denominator, we have x squared minus 5x plus 6, so to factor this, we need two numbers that multiply to 6 and add up to negative 5. Those two numbers would be negative 3 and negative 2. So our denominator factors as x minus 3 times x minus 2. We see here that there's a common factor of x minus 2 in the top and the bottom, so we can cancel those factors out, and that tells me that my function g of x essentially behaves like x plus 7 divided by x minus 3. Now, if we want to know what makes this fraction go to positive infinity or negative infinity, we need to find the x values that make the denominator go to 0, but the numerator not go to 0. Because we've already canceled out any common factors, anything that makes the denominator go to 0 will not make the numerator go to 0. So our next step here is just to set the denominator equal to 0 and solve for x. So setting the denominator equal to 0, we have x minus 3 equals 0. All we have to do is add 3 to both sides. We get x is equal to 3. So this here is our vertical asymptote. Now, I'll also mention that in the original function g, we had this factor of x minus 2 in the denominator. So if x is equal to 2, that's going to make the denominator equal to 0, which means that 2 is not in the domain of our function. And since we won't have a vertical asymptote at x equals 2, when we go to graph this function, we'll have a hole at x equals 2. Let's confirm this by looking at the graph. So let's graph our function here. We have x squared plus 5x minus 14 divided by x squared minus 5x plus 6. We see here that our function just has one vertical asymptote at x equals 3. And if we were to trace our graph, we would see that as we get closer and closer to x equals 2, we'll have a hole at x equals 2. So as long as we factor the numerator and denominator and cancel any common factors, all we have to do is set the denominator equal to 0 and solve for x to find our vertical asymptotes. Let's do one last example. In example C here, we want to find the vertical asymptotes of the function h of x equals x plus 2 divided by x squared plus x minus 6. So first, we want to factor the numerator and denominator and cancel out any common factors. So our function here, h of x, the numerator can't be factored any further, so we'll leave that as x plus 2. Our denominator, if we want to factor x squared plus x minus 6, we need to come up with two numbers that multiply to negative 6 and add up to positive 1. So the two numbers that multiply to negative 6 and add up to positive 1 would be positive 3 and negative 2. So our denominator factors as x plus 3 times x minus 2. In this example, there are no common factors between the numerator and denominator, so there's nothing to cancel out. So we can move on to our second step, which is just to set the denominator equal to 0 and solve for x. So we have the equation x plus 3 times x minus 2 equals 0. Since I have a product of two things equals 0, that tells me that either the first factor equals 0 or the second factor equals 0, which gives me x plus 3 equals 0 or x minus 2 equals 0. On the left here, we just have to subtract 3 from both sides. We get x equals negative 3. And on the right, add 2 to both sides. We get x equals positive 2. Now, these two x values will make the denominator of my fraction equal 0, but the numerator will not equal 0. That's why, as x approaches those two numbers, our fraction will go to infinity or negative infinity. So both x equals -3 and x equals +2 are vertical asymptotes for this rational function. Let's confirm this by looking at the graph. So here we have the function x plus 2 divided by x squared plus x minus 6. And we see here that there are two vertical asymptotes. My first one is x equals -3, and the second one is x equals +2. And we see here that as we trace our graph towards x equals -3, the graph follows that vertical line down. On this side, if we go towards -3, the graph goes up along that vertical line. As we go towards x equals 2, the graph goes down on this side and then up on this side. So in this video, we learned how to find the vertical asymptotes for a rational function.